Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 48, we will start convolution neural network or CNNs. The different concepts that we will cover will be basics, that is CNN fundamentals. We'll start with basics. Then we'll move into CNN architecture, convolution. We will learn about pooling and activation layers. We will talk about the fully connected layers, then the output layer, and then we will discuss an example of CNN, use of CNN in Python. And finally, we will introduce the YOLO algorithm, you look only once, and then we will do a example. YOLO also uses CNN as the backbone, so we will do a CNN example with YOLO as well. So convolution neural networks is a type of deep learning model designed specifically for image processing, pattern recognition, and spatial data analysis. So unlike traditional neural networks, CNN can detect patterns such as edges, textures, shapes in the images. And for example, we can use CNN. CNN is extensively used in face recognition, self-driving cars, medical imaging, and satellite image analysis. For example, detecting tumors in X-ray, this could be done via CNN. Now, why cannot, for processing images and all, in addition to, standard ANN or even MLP that we have learned earlier, so sometimes those algorithms face difficulties while processing images, and which is what CNNs are able to solve. So we will first discuss what are these problems. So for example, in case of images, when we flatten an image vector into a 1D vector with that means every pixel and along with its RGB value is also, all this information is plotted into 1D vector, we lose a lot of spatial information. Along with that, the pixel adjacency relationships, what is near what, that also is destroyed when you create this 1D vector. So the other thing is because we are dealing with pixels, for example, let us take a grayscale image of 100 by 100, that means it has got around 10,000 pixels, and that means if we introduce a hidden layer in artificial neural network of 1000 neurons, that means the total number of weights that we have to compute is around 1000 into 10,000. So that is a huge figure. So this is another concern. The other thing is there is no translational robustness, means MLP learns only for a particular image's pixel specific patterns. Now as soon as this pattern changes, it would be very difficult to identify anything within that image. For example, cat in an image, suppose there is a cat on the left side and there is another image with a cat on the right side. Based on the training, we will not be able to detect a cat because its position has changed. Whereas when we are using CNNs for images, then there are a lot of modifications that actually are being considered. For example, the concept of local receptive fields comes in. A neuron in CNN connects only to a small local region, that is 3 by 3 patch or 5 by 5 patch, 5 by 5 pixel patch, and this allows us to investigate what is there in that particular patch, and is there a feature hidden within that patch, is there an edge, is there a curve, something like that. So we can learn local features and not the entire image together. So this is something which is important. The other is parameter sharing. Unlike MLP, separate weights, where separate weight per pixel is given, CNN reuses the same filter everywhere. That means whenever we are using filters in CNN, that means it is a way to check for patterns and all in the particular image, and we actually are determining the weight of those particular that functions that we will generate out of that, and then those same functions would be, or those same filters would be used again and again. And that will result in lot of lesser number of parameters, because we are not determining weights per each of this pixel, unlike in MLP or ANN. Then there is also spatial hierarchy or hierarchical feature learning. This we have already discussed earlier, that CNN can build such hierarchical representations, such as it can learn about the edges, the textures, the shapes, the objects, or even the semantics if you are dealing with language, right? So all these features could be extracted from that particular set of data. And then finally there is translational invariance, which says detect patterns regardless of their position. That means as long as the pattern is observed in that particular image, wherever it is, doesn't matter, it would be detected, right? So for example, because we are using the same filter to search for the patterns. Now this image gives you the overall idea about the CNN architecture, and this image actually represents handwritten digit recognition. So somebody writes a 2 or a 3 or 4. How do I go about processing, or determining that it is a 2 or it's a 4 or something else, right? So this CNN architecture can be divided into 5 components. Of course, we have to start with the input layer. That is, in this case, it's a black and white image of 28 by 28 pixels, and because it's black and white, so that's why we have only one channel. So otherwise, if there were RGB, that is red, green, blue, all these colors are there, then in that case, and if the size of the image is 128 by 128 pixels, then you can imagine this, and each pixel value could be 0 to 255 based on its RGB value, and so this entire thing has to be represented as a numerical matrix, right? Because the algorithm cannot process if the data is not in matrix form. Now the first step in this particular CNN architecture is feature extraction, and that we do via the convolution layers. Now what it means is we scan the input data using filters or kernels to detect patterns like edges, textures or shapes. So this is the first thing. So of course over here you see I have taken a small portion. This is one filter. Using that small filter, which is nothing but a small matrix, and using that matrix actually represent a straight line, or it represent, basically the figures will be given in such a way which identifies there is a drastic change, right? So using that particular matrix, I can scan the image and we can try to detect some if certain kind of those patterns are there, right? So once that is there, so depending on the number of times this filter is run, depending on how the filter moves from one position to another, then you will end up with lesser number of this output, that is 24 by 24 option, this filter passes would be there, right? Multiplied by n1 means the number of features. So if we detect, we are trying to detect edges or curves, each will be different feature, each would be different, not features, each would be different filters or kernels that we are utilizing. So accordingly that is represented here. We will discuss this in the subsequent slides in detail. Now once we have analyzed using the kernels or the filters, if there are some edges and all these things that are there, we can always keep on we can repeat this particular activity, but before we do that, we actually do some amount of downsampling, or otherwise known as pooling layers. What it means is, from this point, we are moving to this point, but we are doing some amount of pooling. Now what it means? It means preserving key features while reducing computational complexity. This helps reduce multiple dimensions, and one of the algorithm is max pooling, which is the most common pooling method. So that means here we are trying to reduce the dimensions of the data, and how we do that, again you will see that in case of max, we will discuss this in detail in the subsequent slides. So we again we can take from a group of we use a matrix again, and from that we may select from the maximum possible value, right? So that means for each 4 group of data we take we take the maximum value, or we can take the average value as well. For example, we want to do smoothing of image, so in that case we can take average value of 4 pixels, and then we can take and make it into one single value, right? So that is downsampling of the image we call it pooling layers. And finally comes the activation layer, that is the nonlinear function like ReLU is used to introduce nonlinearity like earlier, and this enables the network to learn complex patterns. And once we are done with multiple times of convolution that and then pulling, so we do it in series, so that in one layer we go for very small features, in the other we can go for groups of features, right? So we have already learned this in hierarchical, when we talked about the hierarchical representations and all. And then finally we can flatten, once this is done, then we flatten the and fully connected layer, and once the features has been extracted, the data is converted into a vector and passed through fully connected layers for classification. So that means finally we flatten the entire thing and give, and now we are ready to run sort of a neural network architecture. That means we use again ReLU and all other activation functions, and finally we get a neural network which we solve via backpropagation, and then it can predict the outputs. Now this output layer actually provides a final prediction, and here we can use a sigmoid or a softmax function for classification task. And for softmax we use multi-class classification like cat, dog, horses, and for sigmoid there could be a binary classification such as tumor, no tumor, and so on. Now what is convolution? To explain this in more details, it's a mathematical operation between input data and a filter, right, which is otherwise known as the kernel. It computes weighted sums over local regions and produce a feature map which is otherwise known as the activation map, and this filter is nothing but a pattern detector. So over here you can see this is the filter that we are using, which is again a smaller matrix, and using this matrix we are scanning a particular portion of the image, and when we do that we then do multiplying and summing of the values to which is also otherwise known as convolution, right? And this is the output array. This actually helps us to determine if there is patterns or not. So a kernel filter is a small matrix that slides over an image to detect patterns like edges, textures, and shape. So each filter would be either for shape or for texture or for edge, not all of them together. So it works by multiplying and summing values in small regions of the image, which is otherwise known as convolution. And CNNs you can use many filters, each learning a different pattern, and filters are not predefined, and these are learned automatically during training using backpropagation. And over time filters become specialized pattern detectors, helping the CNN recognize complex features and objects. Now this is the mathematical formulation for that, where Sij is the Si comma j is the output feature map value at position ij, and this portion where the input image pixel value at the shifted location and the kernel filter weight, both of this together is taken and multiplied and summed up, and then the value that we get is the output feature map value at position I and j. So that is what it works on. So what we are doing is we use a kernel filter or a small matrix to scan the input data from the image and extract special features like edges, textures, or shapes. Each filter learns to detect specific patterns based on the nature of this particular matrix. When we run it, if it gets to a value, that means it is identifying a pattern. And then and we can do it in we can use very small matrix, either 3 by 3 or 5 by 5 with learnable weights, and the weights actually get trained. And for this and how this filter moves across, it is decided by stride, with the step size of the kernel sliding across the input. Strides could be 1 or 2. We will just show that in the next slide. And then we can also add zeros around the input to control the output size, and this which results in retaining the same dimension of the output from the input. So and finally we get the output feature map, which and the total output size is basically input size minus kernel size plus 2 times padding divided by stride, and overall we add 1 to it. Now stride is basically, it is how many steps the filter moves at a time. A higher stride reduces the output size because fewer positions are covered. So as you can see here, the stride is 2, so the output is also reduced, whereas here the stride is 1, so the output is reduced but not that reduced. And padding is like adding a border of zeros around the images before applying the filter, because as you can see the filter moves across, and but if we add a border of zeros, then in that case we will not lose the edge information. Otherwise the edges are passed very only once, right? Because next time when the filter passes, it will not again come back to the same position. But if you go over a single thing multiple times, maybe we can detect a pattern so that each pixel is connected with another pixel and so on. So that means if I can do a little bit of padding, then probably I will not lose some information. So stride basically controls the output spatial resolution, degree of downsampling, and it also reduces the computational cost. That means if we give a larger stride, the computational cost would be less. Whereas padding controls, it maintains output size across the layers. We try to do that, right? Because if we are using padding, then the output remains same in size. It preserves edge information, enables deeper network architectures, and keeps spatial resolution intact for longer. That means the spatial resolution, that means because we are maintaining the size, the spatial resolution remains. Now, then comes pooling. Pooling layered, what it does is it layers down sample feature maps to retain dominant features while reducing the computational complexity and overfitting. And these are translation invariant, means sensitive to small shifts in the input. Now, there are two types of pooling. Over here you can see the max pooling function, and it is performed over a 4x4 feature map with a 2x2 filter and stride of 2. And the output of max pooling operations, you can see that after the max pooling, we have taken the maximum value from each one of this. So this becomes 8, then this becomes 6, and this becomes 9, and also this becomes 9. So here we are keeping the maximum value, but we can also go for average pooling, where we can take the average of the entire window and then we can also store it. Of course, there is the activation layer. Activation layers introduce non-linearity to the network. This allows us to learn complex patterns. We have discussed this earlier in much detail. And without them, the network would only model linear relationships. To introduce non-linearity, we are using the activation functions. And these are mathematical functions applied to each neuron in the neural network to determine whether it should be activated based on its input. Now, we have several activation functions. The most popular ones are ReLU, rectified linear unit, where either the value out of the values on which we run the function, if x is greater than 0, it stays the same. If x is lesser than 0, it becomes 0. It is good for deep networks and it is very commonly used. Now, leaky ReLU is almost same. Only thing is, in case, but instead of making negative value 0, it converts them into something very small value. This actually helps us to avoid the dead neurons. And then there is sigmoid function, which we have also learned earlier. Output is between 0 and 1. So if there is a probability task, that means we want to get the probabilities at the end, we will probably use this sigmoid function. And then tanh this is better than sigmoid, because for hidden layers it allows negative output. So because the output is something between the range of -1 to 1. And finally, once the activation functions are used, then finally we move on to the fully connected layer, and this is used in the final stage of the neural network to predict. They take all the extracted features and use them to determine the correct class or output. So that means this is the final pulled feature map after all the different this pooling and all the different this convolutions that has happened. Once that value we get, so after that we have to flatten it into into a single one-dimensional vector, and then the extracted features from previous layers like convolution layers are in a usually in a multi-dimensional format, say 3D format of 7 into 512. So flattening will convert this into a 1D vector, which can be used as this fully connected layer, and this image would be having around 25,088 elements, because we have to multiply 7 into 7 into 512. And so this would be stored in an 1D array, and then all this we can using this array this becomes the neurons, and we can determine the weights, and every neuron in the layer is connected to all neurons in the next layer as we design this particular neural network. And these layers learn patterns and relationship between the extracted features and the final outputs. So this is where this is how the overall convolution neural network works. The output layer produces, of course, the final prediction. Again, same as the neural networks, we use activation functions which would be used at the end, and it would be tailored for what is the prediction task, if it is binary or is it multi-class. So if it is binary, probably we go for sigmoid activation. which help us in binary classification, which we learnt earlier. If it is multi-class, then we go for softmax classification, where which converts the logits into probabilities across classes, and raw scores logits will be converted into probabilities, ensuring that everything will be added up to 1. And this actually helps us to predict, what are using the softmax function, that if these are the 4 input the scores, the raw logit scores, then these are the probabilities of each of these scores, and from there we can predict what is the probability. Based on the probability range, we can predict which class this particular feature belongs to, right? So which class this particular data point belongs to, and then we can predict it's a cat or a dog, whatever the case may be. So this is basically same as what we have done earlier. That means once we have computed the overall score, z equal to WA plus B, and for the different this inputs from the previous layers, and then we use the activation function to get to the output layer, or where we predict the classes. Now coming back to that image that we started with, now that we know all the different steps in detail, let us see how this actually gets translated or can be explained in this particular image. So in this particular image, we are seeing the input layer to be 28 by 28 into 1. 1 is, it's because it's a black and white image, so that means there is only a single channel, grayscale. And then the first convolution layer, con 1, so we have got 2 convolution layers over here. So the first convolution layer is a 5 by 5 filter applied to extract features, either edges, curves, stroke patterns, and so on. And so padding is valid, that is no zero padding is added in this particular layer. And then output size is 28 minus 5 plus 1, which is the formula that we used from earlier. So this comes to around 24. That means that's why there are 24 into 24 into n1. This number of n1 is the number of channels or the number of filters or feature maps, right? So this is the output which goes into the next layer, where we do the first maximum pooling layer. For each 2 by 2 region, the maximum value is selected. So for example, out of this, we will select 4. So output size from 24 reduces to 12, because once we run the pooling function and then get to a smaller score, we get only 12 by 12 this output size, and final output is 12 into 12 into n1. And second convolution layer, again we are using another kernel size of 5 by 5. Padding is valid. More complex patterns such as parts of digits, curves, or stroke combinations can be detected. And output size is 12 minus 5 plus 1, which comes to around 8. So the output is 8 into 8 into n2, which is the number of filters in layer 2. And depending on the number of filters, we can have this n2 value can vary, and similarly n1 value, n1 can also vary. So second max pooling, 2 by 2 pooling is applied. Size reduction becomes 8 to it becomes 4. So output is 4 into 4 into n2. Finally, we go for flattening, which is the last part. That means the 3D feature maps are converted into 1D vector. So 4 by 4 into 64. In this case, it becomes 4 into 4 into 64, 1024 element feature vector. And then because this is the number of this n1 value, so this is the final n2 value. So this is the total number of filters, and we are getting 4 into 4 into n2 over here. And then this connects the CNN feature extracted to the classifier finally. So the fully connected layer or the dense layer, here we are passing the flattened features to a fully connected neural network with ReLU as activation function, as we have done earlier. And this both combine extracted features and help learn the classification boundaries. And sometimes we also have something called a dropout layer, which you can see over here. You will see this being used in many programs. Now dropout basically means in a fully connected network, sometimes we can turn off some portion of the neurons during training, and this actually helps us to achieve generalization. That means 20 to 50% neurons are ignored in each iteration, and this would prevent overfitting and improves generalization. So the final output layer contains 10 neurons like 0 to 9. Softmax activation actually converts the outputs into probabilities, and these probabilities could be represented like for 0, this is the probability, 1, this is the probability, for 2, this is the probability. As you can see, this has got the highest probability, and we can predict this belongs to class 2. So now coming to an example in Python. So to use this particular program, what we are doing is we are using a data set which is already available, available in Torch Vision. It's the Eurostat database. What it has is it has got many images which actually contains images of different land surfaces, and also it has got the labels which are the different classes, right? So that means the classes is basically the what are the kind of land covers. So like forest, residential, annual crop, and so on, right? Then permanent crop, forest. So these are the different classes as per that particular data set. Now we are importing Torch, which is the main framework here. NN is the neural network layer in that, and then Optim is the optimization training part of that. Then we are importing Torch Vision, which is the built-in data sets, and then we need to convert the images into tensor format. That means so that it could be we can process this particular data, and this import Torch Vision.transform as transformed allows us to do that. Then the rest is like within Torch we can do the random split of the data for training testing. That part is imported. Then matplotlib pyplot as plot, numpy as np, sklearn we are importing the confusion matrix, and then also importing cbon and sns. So first we are printing download real Sentinel-2 satellite data Eurostat. This is just a line getting printed, and then what we are doing is we are directly transforming and storing the data to a tensor. That means we are converting it to tensor, which is an array. So tensor transformation converts raw images of with pixels 0 to 55 range into normalized PyTorch matrices of 0 to 1 range, right? So this preparing and this help us to use them for mathematical operations. So this is what is first happening. That means I am storing all the images in my tensors, right? So once we do that, and that first we are informing about that, and then actually we are converting it over here. So Eurostat data equal to Torch Vision.dataset, and then this is where it is stored. Download is we first have to download it if it is not there, and then you will see when you run the program that the data set gets downloaded, and then we can transform it. So then we extract the class names from the data set. So these are the labels from the data set. That means for the different images already the labels are there. So we store those first over here, and then we decide the train size, which is 80%. Test size is the remaining one, and then what we do is then we randomly split the data, which 80 and 20 is fixed, but we randomly pick up values from the data set for training and testing. And then what we do is we do something called batching. So over here you can see the data loader is being called, where the batch size is 64, which actually means that data loader fits the network in optimized chunks of 64 images at a time, shuffling the training data to prevent the model from memorizing sequence patterns. So this is a way to prevent overfitting. So this is where we are. This entire code is actually written to extract the images and then actually show that in a plot. And you can see that we are also giving a subtitle to that, and then we are using a title for that, and we are for different images we are extracting, and then we are storing it, and then we are also changing its shape. Now what changing its shape means, when in PyTorch where we have saved the image earlier, so it is shaped as channels, heights and width. So the np.transpose function actually restructures this into height, width and the channel. Height, width means the height of the image, the width of the image in pixel widths, of course, and channel is the number of colors, right? So that means this we are doing a transport so that MATLAB can render them visually, because MATLAB will take it in this particular format of input, right? So once it is done, then we can plot it, and once we can plot it, we can also show the images, and we can give the class names as well to that. So that is what has happened over here. So these are the images we are downloading, and we can see some of them over here. So then we run the model, the CNN model, which is over here. So nn.sequential is the CNN architecture. Overall, this is what we are building over here. And so in the block 1, that means we are doing feature extraction, the first convolution layer. So here we are starting with 3 channels, which is RGB is there. So there are 3 channels over input channels. These 3 colors of each pixel has got these 3 colors for those. Then 16 we are using 16 filters, out channels 16, which indicates that there are 16 filters are used for learning 16 features, either edges, textures, and so on. Then padding is equal to 1, so that means size will remain same. So it will remain 64 into 64 will remain 64 into 64. Then max pooling, we are utilizing max pooling over here. So here the kernel size is 2 and the stride is 2. So it will reduce 64 to 64 becomes 32 to 32. And finally, because there are 16 features or 16 filters, the output is 32 into 32 into 16. Now this again goes into block 2 to detect the higher level patterns, and there the 16 feature maps becomes 32, output becomes 32 feature maps, and it detects more complex pattern like shapes, land features, and so on. So the size change from 32 to 16 into 16, and the total output is 16 into 16 into 32. So this 32 is the number of kernels that we are going to utilize, right? And because of pooling, we are reducing from 32 to 16. Now finally, what we have to do it, then the data then this particular output is flattened, and we automatically flatten the 32 channels into 16 by 16 grid. Then NN linear, we are running this is where we are totally flattening it out. So 32 into 16 into 16 become 8192 incoming connections. We are using ReLU as the activation function, and then we are getting 10 output nodes for the 10 Eurostat classes that has already been designed. So that means we are starting with 120, and eventually there are 10 this outputs, and then we are using this cross entropy loss as the loss function, and we are using Adam as the optimizer, which earlier we have also utilized, right? And there are only 5 epochs that we are working with. Of course, you can give it much more epochs for better training, but 5 epochs for this point is okay. And so this is where the training starts. So once the training starts over here, for each epoch we are first storing the values as 0, that running loss, correct, total is 0. Then as we are running the epochs, we are again storing this values. We are the data that means first we cleared the previous gradients, and then automatically we can data flow straight through the sequential blocks one after another, and then we get the model. We are getting the model, we are running the model, and we are getting the output. The criteria we are using, the loss criteria we are using, and the loss backward and optimizer dot step actually tells us that every time the loss function is actually also updating the weights. The optimizer the step actually updates the weights using this particular weight update, and it adjusts the internal filters and weights to improve the accuracy of the next batch of data. And forward and backward pass, the model predicts the class outputs, the criteria calculates the exact error loss, and the loss backward calculates the gradient via back propagation. So so this is how it goes on, and once the training starts, you will see because we have given verbose somewhere, I think. So we can see that epochs, what is the training happening, what is the loss, what is the and what is the accuracy levels that we are also printing, that is getting printed over here. And then for each we are making sure that the final, like after 5 epochs, the accuracy is around 77%. So we can keep on increasing the epochs, and then we can get better results. Finally, we are printing the model, and we are first predicting using the model, and then we are printing the results, of course. And so first we are evaluating model on unseen test data and the test set that we have already stored earlier. And in the inference mode, that is model eval and torch dot no underscore grad freeze this one particularly no underscore grad freeze the network, disabling training specific functions and saving memory during testing. So this is not that important, but we are doing granular assessment, which is instead of relying solely on global accuracy percentage, the confusion matrix maps every prediction against its true level. The resulting seaborne heatback allows to visually diagnose exactly which land cover losses classes the model struggles to differentiate. So first we are predicting. Once we are predicting, we are storing the results, and once we are storing the results, that means we are also checking if the predictions are how much it is correct, right? So we are creating a heat map which is done in this particular code. You can always test this on your own, and what we are doing is at the end of that we are getting a plot which looks like this. Final accuracy is 79.35%, as we have already found out, and this plot, heat map plot, actually tells us that for each of these particular classes, this side is the actual class and this side is a predicted class. So if actual class is annual crop, then, and also predicted class is annual crop, that means 519 are predicted correctly. And you can see some of this annual crop is none of them are predicted as forest. Some are predicted as herbaceous vegetation, some are predicted as highway, some are predicted as pasture, and so on. So this way we have to read this, right? So we find that if this is the diagonal which is the prediction of the same class to same class, so this shows that we have very high accuracy of prediction. The dark blue concentration confirms that CNN successfully learned spatial patterns to correctly classify most land cover types, and there are some systemic errors. So misclassifications are not random, they occur between visually similar classes such as highway versus river, where we will see that this is the river and this is the highway, right? So over here you can see that in many cases only 291 highways are being classified as highway, whereas many of them would be classified as river. And then over here, if it is river, you can see many of them are probably classified as highway. So 57 of them are classified as highway, right? So this is because the images look similar. And then homogeneous natural features like forest achieve the highest accuracy, whereas highly variable human-made environment like industrial zones show wider error dispersion. So these are some of the interpretations of the results that we get from this particular model. Now finally, we will also discuss briefly about YOLO algorithm. You only look once, that is the long form for YOLO, and it's a real-time detection algorithm based on CCTV footage. People use it to detect vehicles or people or images or certain any other features that you want. The YOLO is the first one-stage object detection algorithm with real-time capabilities. It is of course trained for vehicles and all, but we can follow similar kind of algorithms to detect other things as well. It divides an image into a grid, predicts bounding boxes and class probabilities in a single forward pass using a convolution neural network. So that means it divides the image into a grid. That is the first step. Predicts bounding boxes means it will for different features it will put a box around it, and also it will predict what class it belongs to. Is it a car, is it auto rickshaw, and so on, right? And this is done in a single forward pass and using a CNN, right, convolution neural network. So of course you have to install the required libraries first. Ultralytics, OpenCV, these are the two libraries you need to install. Then load the pre-trained YOLO model. That means we are not training the model here. We are already it is already done. So we are just utilizing the model for our prediction. So this we have to install, and then automatically it will get downloaded, and then process CCTV video frame by frame. So we need to give it a CCTV feed, and then this we can adjust the the frames per second, those kind of rates and all. Or after that we have to also adjust the image, like the perspective of the image, or we have to flatten the image to find the actual location of that particular item in that particular image from because from perspective you have to do the transformation so that it seems like we are looking at the image from the top. And then we run YOLO for each frame, and we extract features, and then once we have done, then we can also visualize the final output, or we can store a video with those boxes and so on. So the YOLO architecture is like convolution layers extract key features like edges, textures, shape. Then feature maps are passed to multiple layers to detect objects of different sizes. Then bounding boxes and class probabilities are predicted in one forward pass, and then non-maximum suppression removes duplicate detections, post-processing steps to eliminate overlapping boxes. So this is where we gave a IUU threshold of 0.5 by default, or we can set our own values. And so this is just to make sure that there are no duplicate detection or no overlapping prediction and so on. And final output includes object level confidence scores and bounding box coordinates. And YOLO V8 uses a CNN based backbone, cross stage partial network CSPNet, and for feature extraction and detecting head for predicting bounding boxes and class probabilities. So this is how the program looks like. So we have to install Ultralytics, and we have to import CV2. If you have not installed that, you also install that, import that, or install that. And then supervision is for advanced tracking, and then OpenCV is for matrix transformation. So these are the different libraries that has been installed. Then we have to give the vehicle the video paths which will be analyzed. So this is the vehicle video.mp4 which is stored in the root directory. So that is being given the path, and this is the result video. That means once the algorithm processes this particular video, it will create a new video with those bounding boxes and so on. So this actually helps us to do that. And then we are setting the confidence threshold as 0.3, IOU threshold as 0.5. The model name is given over here, model resolution is given, and this is basically we are configuring the hyperparameters, and confidence threshold at 0.3 rejects low certainty detections, and IU threshold 0.5 to prevent overlapping duplicate boxes. And finally, we have to determine the 4 corners of the polygons on the video. That means because the video is a raw file, we have to exactly tell that from which portion of the video from where we will extract the features and all. So that is what is being done over here. So this particular the coordinates or the from the based on the pixel values are given, and then target projection, the physical space define the real world metric dimensions for the exact the area for which we are going to work. So that is given over here, and then once what we have done is we are doing this this transformation architecture. That is, we define a custom class to handle the spatial conversion from a skewed camera angle to a top down metric plane, because we are looking at, because if this is a road, the camera is actually mounted over here. So we are looking like this. So it's a skewed plane, right? So from there we have to make sure that we do mathematical transformation so that the image which we are looking at, because we would usually have a front view image or something like that. So then we have to convert that so that it is in the top down metric plane. So that means how it looks over in this, in this layer, in this particular top down vision. So that conversion has to be done. So that is being done. And so these are extra tasks. That is, we have the trained model, but we have to put the data in a certain way to that particular model. And then over here, what we are doing is we are doing the homography matrix computation, which utilize CV2.get perspective transform to compute the mathematical mapping between 2D camera pixels and that 3D ground plane. So that is what we are talking about. And finally, we are calling the YOLO model, and then we are running based on the transformed video, we are running the YOLO model on that. Now, not only that, once we have run we are running the model, we have to also we do certain other things. For example, the byte track algorithm, this assigns unique mathematical IDs to detected vehicles and maintains their trajectory across sequential frames even if temporarily obscured. So that means these are additional tasks that we are doing. That means we are not only identifying the vehicle, but we are tracking it over several frames, and we are also maintaining that. So that is what the byte track algorithm does. And then polygon zone is to strictly confine the detection pipeline to the predefined roadway, actively ignoring the background motions and all these things. So that is the task of that. And then finally, we execute YOLO on the current frame. And once we are doing that, that means we can use the confidence filtering and all this thing is automatically done. That means we discard any detections falling below 30% confidence baseline, and we also exclude specific YOLO classes that we want to remove predictions from the model. Then we will also specify that, but we want to keep predictions, that also could be kept. So if we are counting vehicles, we can do this, but if we are counting pedestrians, then we will probably remove the vehicles. And then zone and overlap filtering, this also is basically help us to prevent this prevent to check the overlapping is happening or not, right? So finally, we extract the bottom center coordinates of each bounding box representing the vehicle's exact point of contact with the asphalt. So that is what we are doing, and we are detecting that part, and then we are once we are transforming this, we are passing this raw pixel coordinates through the view transformers to acquire their real world metric positions in that particular image, in that particular frame, and then store the vehicle's coordinate history in a rolling queue bounded temporarily by the video frame rate, and from this we can actually calculate the velocity, and also finally we can annotate the frame with this particular bounding boxes and so on. So bounding box rendering is done. Superimpose dynamic distinct bounding boxes on the tracked vehicles utilizing SV box annotator. So that is being done over here, and then the telemetry is displayed. We utilize OpenCV's dot put text to overlay the computed real-time speed and unique tracker ID directly above each vehicle, each box. So for each box we will add the vehicle ID and the speed of that vehicle, and then we can also do frame-wise compilation, sequentially write each fully annotated frame into the video sync, compiling the final output video. So that means once we have done that, once we are done all this, put all the data that we want into the frames, then we can write the frame and we can save it in form of a video. So this is how it looks like. So the analytical boundary basically is a distinct red polygon delineates the calibrated region of interest on the roadway, visually confirming the specific metric zone where the perspective transformation is active. So this bounded area is what we are dealing with. Then dynamic bounding boxes is vehicle entering this region of interest are actively tracked and highlighted within the bounding box, and the real-time telemetry actually tells us that above each vehicle an alphanumeric level displays its unique tracking identifier alongside its estimated physical speed in kilometers per hour, and calculated continuously as it traverses the defined matrix grid. So this code actually help us to run the yellow model to detect vehicles and pedestrians, of course, but pedestrians is ignored in this particular part that we have specified. And what we are doing is we have to specify the road width, the area for which we are setting up this particular analysis. We have to also set up change the because of the camera angle, we have to make it sure that everything is we are looking from a top down approach and so on. So for that mathematical we have to change that particular coordinates and all. So those things are all done, and eventually you will get an output something like this. So the raw image didn't have any of these bounding boxes and anything, but after this we have run the model, we get an image where we can get this particular figures, right? So this could be done even in real time as well. So the processed output video provides a comprehensive visual synthesis of the object detection, tracking and velocity estimation pipeline. So these are some of the references you can use. To conclude, convolution neural networks enable machines to automatically learn hierarchical spatial features from images, making them one of the most powerful tools for modern computer vision and intelligent urban sensing applications. Thank you.